A star in the Andromeda galaxy didn't explode. It didn't flare into a supernova. It didn't leave a bright corpse you could point a telescope at and say, "There it is." It just faded, and then it was gone. And for the first time, astronomers have a strong, observationally backed case that what we're looking at is a star collapsing into a black hole, without the fireworks. The evidence was published in Science on February 11th, 2026, by Dr. Kishalay D. and his team at Columbia University, after they assembled over a decade of infrared and multi-telescope observations into a single, coherent story. Here's the promise of this video. We're going to reconstruct how you watch a star die when it refuses to put on a show, and why this kind of death might be hiding a huge fraction of the black holes in the universe. And because the scary part isn't that one star vanished. The scary part is the implication. This could be happening all the time, and we've been missing it. So let's start with the simplest question. What does it mean for a star to die without a supernova? Most people learn a clean story. Big stars run out of fuel, their cores collapse, the shockwave succeeds in blasting the star apart, and the result is a violent explosion, an expanding shell of debris you can see for months, sometimes years. That's the classic core collapse supernova, and it's real. But the shockwave succeeds is doing a lot of work in that sentence, because there's a darker option, a failure mode. In some collapses, the shockwave doesn't have enough energy to blow the star apart. The core keeps falling inward, and what's left behind tips past neutron star physics into something even more final, a black hole. According to D and his colleagues, whose findings were published in Science, this is what astrophysicists call a failed supernova, where gravity dominates and the star's outer envelope is only gently ejected rather than explosively expelled. That phrase, gently ejected, is the key to the whole mystery. If you're waiting for the sky to light up, you may see nothing. And that means a star can die in a way that looks, from 2.5 million light years away, like someone dimmed a cosmic lamp and quietly walked out of the room. Now, meet the lamp. The star was called M31-2014-DS1. It lived in Andromeda, our nearest galactic neighbor. In its prime, according to Dr. D's team, it was one of the most luminous objects in all of Andromeda. But a yellow supergiant, roughly 13 times the mass of our Sun. According to Columbia University's official account of the study, this star brightened in infrared light, stayed bright for around 3 years, then faded dramatically and disappeared, leaving behind only a shell of warm dust. And here's where the story gets strange. This wasn't some new event everyone was watching in real time. The data already existed. It sat in archives. The telescope saw it. But it took years for scientists to piece together what had actually happened. So how do you go from a weird light curve in old infrared data to, we probably just watched a black hole being born? You do it like a forensic investigation. You don't look for one dramatic piece of evidence. You stack many small ones until the alternative explanations collapse under their own weight. And the first piece of evidence is the timeline. Archival data from NASA's NEOWISE mission, the Near-Earth Object Wide Field Infrared Survey Explorer, which completed its 15-year mission in 2024, revealed something unusual starting in 2014. The star was brightening, not in visible light, but in infrared, a slow, warm glow that built over several years. Then, according to the NASA/JPL press release on this discovery, the brightness dropped sharply around 2016, and by 2023, the star had effectively vanished, faded to roughly 1/10,000th of its original brightness. That's not what normal variable stars do. That's not what a simple dust puff looks like. And it's not what you expect from a star that's still alive and burning. Now add the second piece. Where did the energy go? And if the star is gone in visible light, but something still glows in infrared, that points to dust. Dust absorbs higher energy light and re-radiates it as heat. According to the Keck Observatory's press release on this study, a faint infrared glow remained, consistent with leftover gas and dust, still warm, still slowly expanding outward from the collapse site. So the picture looks like this. The core collapses. The outer layers don't explode outward with supernova violence, but some material is gently expelled and forms a slow-moving dust cocoon. As it expands and cools, the infrared signature evolves in a way telescopes can track over years. But we still need to eliminate the imposters, because a star disappeared has alternatives. One serious possibility: the star didn't die at all. It simply got hidden. Maybe it's still there, and wrapped in a thick cocoon of dust that blocks visible light. That's not a fringe idea. We know dust can completely obscure massive stars, even bright ones. So how do you tell hidden from gone? Think of it this way. A star hidden behind dust is like a fire behind frosted glass. You still see the glow. What the team found was more like switching the power off entirely. You look across wavelengths simultaneously, and you look for consistency. According to the research published in Science, Dr. D's team followed up using the Keck Observatory in Hawaii, the Hubble Space Telescope, and JWST, observing the site across infrared, optical, and ultraviolet wavelengths. Dust behaves differently at each wavelength, and a star hidden behind dust would still emit energy at longer infrared wavelengths in a pattern consistent with a living stellar surface. What the team found instead was a total spectrum dimming, brightness collapsing across all wavelengths simultaneously. That is the critical fingerprint. A synchronized, complete fade across every wavelength indicates only one thing: the energy source itself switched off. Nuclear fusion stopped. And the only mechanism that does that is core collapse. Now, before we look at exactly what happened in those final seconds, pause and appreciate the observational weirdness of this crime scene. We are talking about a star 2.5 million light-years away. Every photon in Dr. D's dataset is ancient. The moment M31-2014-D S1 collapsed had already happened long before our species, Homo sapiens, walked the Earth. What the Columbia team is doing isn't just astronomy. It's reconstructing a disaster from delayed light, reading a cold case file written by the universe itself, delivered at the speed of light, 2.5 million years late. And here is what that file says happened in the final seconds. The star's iron core, the dead-end product of a lifetime of nuclear fusion, ran out of road. Gravity, which had been held back for millions of years by the outward pressure of nuclear burning, finally won. In under 1 second, the core collapsed to roughly 20 kilometers across, the size of a city. Normally, that collapse sends a shockwave ripping outward through the star's layers, detonating it as a supernova. But here, according to Dr. D's team, the shockwave stalled. It ran out of energy before it could break the star apart. And instead of an explosion, you got a much weaker ejection. Co-author Dr. Andrea Antoni, also at Columbia, described the energy released as roughly 1,000 times less than a standard supernova. This is exactly what gently ejected means, made concrete. Not an explosion that tears the star apart, but a weak push, a final breath rather than a detonation. So you end up with two simultaneous outcomes. Most of the star falls inward and becomes a black hole, and a smaller amount of material drifts outward, cools, and becomes the dust cocoon that NEOWISE spent years quietly recording. That dust shell is your only clue that something extraordinary happened here. Without it, there would be nothing to find at all. Now, there is a competing interpretation, and it deserves an honest look. In January 2026, just weeks before the science paper was published, Professor Noam Soker at the Technion, Israel Institute of Technology, posted a detailed analysis to archival, the preprint server used by astrophysicists worldwide. His argument: the failed supernova interpretation for M31-2014-D NES1 requires what he calls unlikely, fine-tuned parameters. In his reading, the pattern of infrared brightening and slow fading is more consistent with a violent binary star interaction. Two stars in close orbit, one ejecting a massive dust shell during a close encounter. This is not a fringe view. Soker is a credentialed researcher, and his challenge highlights genuine uncertainties, particularly around how the ejected material's timing and energy budget fit the collapse model. Dr. D's team points to the total spectrum dimming as the key differentiator. No binary interaction can simultaneously extinguish a star across all wavelengths from visible through infrared. And as of February 2026, no rebrightening has been detected at the site of M31-2014-DS1, which is exactly what the failed supernova model predicts and what a binary interaction would struggle to explain. The jury is not fully in, but the evidence right now strongly favors the black hole interpretation. This discovery didn't come from nowhere. There's a history behind it. For years, astronomers have known something was off with the stellar death books. When you count the massive stars that should be exploding as supernovae, and then count how many supernovae actually occur, the numbers don't match. There are fewer explosions than there should be. And one explanation that gained traction in the 2000s: some massive stars skip the explosion entirely. They fail. They collapse directly. But the problem was always evidence, actually catching one in the act. The first serious candidate came in 2009 in the galaxy NGC6946, nicknamed the Fireworks Galaxy for how often supernovae occur there. A red supergiant, now called N6946-BH1, brightened briefly, then disappeared. According to research published in the monthly notices of the Royal Astronomical Society, the disappearance of N6946-BH1 remains consistent with a failed supernova. But the data was limited. The pre-collapse record was thin, and the timeline was incomplete. M31-2014-D S1 is different. Andromeda is 2.5 million light-years away, versus NGC6946's 22 million. The data is richer. The timeline runs from 2014 to 2023. And critically, the full sequence was captured: pre-collapse infrared brightening, multi-wavelength fading, and continued darkness afterward. According to the Columbia University press release, this represents the most detailed observational chain ever assembled for a direct collapse event. Reuters called it the best evidence yet of black hole formation without a supernova. So what comes next? Two things. First, long-term monitoring. The faint infrared glow at the site of M31-2014-D S1 should fade steadily over the coming decades as the dust shell expands and cools. According to NASA's Jet Propulsion Laboratory, Dr. D's team is continuing to monitor the location. If the collapse interpretation is correct, the site stays dark. Any rebrightening, any return of optical or infrared luminosity would demand a completely new explanation. Second, scale. Now that astronomers know what a quiet collapse looks like, the infrared brightening, the multi-year fade, the total spectrum disappearance, they can search archival surveys for similar signatures elsewhere. According to the NASA/JPL press release, the team has already identified a second candidate, another massive star in a nearby galaxy that may have undergone the same process. And if candidates start accumulating, the story shifts from a rare anomaly to a missing population. That would ripple outward into everything we thought we understood. How many black holes exist in galaxies like ours? How often massive stars truly explode versus quietly collapse? And how much of the universe's heavy element production we've been correctly attributing to supernovae? The Vera C, a Rubin observatory in Chile, now operational and scanning the full southern sky every few nights, is positioned to revolutionize this search. Its sensitivity to stellar transients means it may reveal dozens of failed supernova candidates within the next decade. We are entering the era where silent stellar deaths are no longer invisible. For most of human history, a star was the definition of permanence, a fixed point, a nightly constant. But in February 2026, a paper in Science made a different kind of permanence feel real, the permanence of disappearance. The idea that a star can live for millions of years, then, without a visible explosion, simply stop being a star at all, leaving behind an object that emits no light. A black hole birth you don't see, you infer. And maybe that's the deeper lesson. But the universe isn't only spectacular when it's loud. Sometimes the most important events are the ones that force you to notice what's missing. Because out there, in a neighboring galaxy, a star ended, not with a bang, but with a fade to black. And we finally had the instruments, the archives, and the patience to read what that silence was trying to say.